So hi everybody. First of all, I would like to thank the organizers and especially Tali Tishby for inviting me to this wonderful conference here. So I'm going to talk about mathematical aspects of embodied intelligence. So it's like an empty title, and because I was asked at a point where I didn't know what to talk about. So the content will be filled afterwards. So this is the content of my talk. I will start with the motivation of the field of embodied intelligence, in particular the notion of cheap design. This is a notion well known within that field, and I want to propose mathematical formalizations of that notion. That formalization will be based on the formal model of the Sensorimotor loop, which is actually the model that Tali presented on Monday. This is a very general approach, but we will exemplify this approach by using restricted Boltzmann machines. So I will spend some time on the geometry of conditional restricted Boltzmann machines as models for policies. Then I will come back to the notion of cheap design using conditional restricted Boltzmann machines and show you how the theory works in an experimental case study. Finally, if time allows, I will mention the simple grounding problem within the field of embodied intelligence and its relation to Uexküll's concept, Umwelt concept, and I will propose a mathematical approach to formalize that concept. So let me start with a simple motivation. Let's consider this system here. It consists of 7 simple robots. Each of these robots looks like this. It has 2 wheels. And it's controlled by a very simple neural network, which consists of 2 input and 2 output neurons. So this is the brain of that tiny robot, and all of these robots have the same brain. And so we look at the behavior of these robots, and they don't seem to show any structure in their behavior. It's like a Brownian motion. But now we couple these robots together in terms of physical couplings, and we don't change their brains. So this chain here consists of different physical bodies, so to say, but it has the same brain. Each of these elements, small robots, have the same previous brain. And now, if you let the system run, it suddenly displays some kind of coordinated behavior. So the astonishing thing, at least to me, is the fact that there is no central control. So the whole coordination comes from the physical coupling of the segments. So all of you know, of course, distributed versus central control, but in this context here, I'm using that example as a...
Are these neural networks training or are they fixed?
Okay, that's a good question. So the thing is, we obtained this example as a result of a maximization of predictive information, which I'm not going to talk about, but this is exactly the quantity that Tali was talking about on Monday. So when you train these robots in the chain to maximize their predictive information, which is completely intrinsic to the system, you get the emergence of some coordinated behavior. And then after having that, so as a result of a training, of a learning process, then you decouple the system and don't learn anymore. I'm just showing you the result of that learning process, which is on the right-hand side. But what this means is that if you train the system and it starts to coordinate for some reason, okay, and then you change the physical properties, it doesn't display any structure at the behavioral level anymore. So the training or the optimization is really within the context of the physical constraints. Okay, but I'm not going to talk about predictive information today. So this illustrates the concept of cheap design within the field of embodied intelligence. So it basically says that systems, biological systems, should exploit the properties of their body in order to generate behavioral patterns. They don't have to coordinate all the behavior with the brain. The task of the brain is not to control the body, it's to exploit the properties of the body in order to express the desired behavior. And the extremes version of this is the so-called passive dynamic walker. It is a mechanical system designed to show a nice, naturally looking walking behavior without any control. This creature doesn't have a brain, so it doesn't control the walking. So, and this is quite astonishing, even though if you look at it, it's trivial that it's possible. It's basically you have a slope here, and the system is falling all the time, and while it's falling, it's showing this nice walking behavior, but it doesn't have a control. So what does this mean? It obviously doesn't mean that we don't need our brain, but it does mean that it's possible to exploit the properties of your body. And the big challenge is to understand this exploitation process and to derive principles for designing artificial systems that do actually exploit the properties of our body, which means, or the association that we have while pursuing this path is that we can design concise control architectures that actually generate the desired behavioral patterns. So as I said in the beginning, I deeply believe that this challenge can be addressed by using a formal model of the Sensorimotor loop, which I'm going to talk about here. So as Tali already nicely explained in his introductory lecture, we consider the Sensorimotor loop basically describes the causal interaction of the world with the agent. This C stands for controller, so with the internal state of the agent, through sensing and acting. And that's the causal diagram, what we call the causal diagram of the Sensorimotor loop. But the causal diagram is not just a diagram, it's a Bayesian network. It has a structural component, which is this one, and it also has a more quantitative component, which describes the mechanisms of the Sensorimotor loop. So in each node, you have so to say, a Markov kernel or stochastic matrix, which describes the mechanisms of that node. So for example, beta describes the sensory mechanism. Then you have the phi, which describes the internal dynamics mechanism. You have the pi, which is the policy. And then you have the alpha, which describes the dynamics of the world. So all of this are described in terms of, most generally in terms of so-called Markov kernels, which are simply conditional probability distributions, but used as a generative model. So what is important to note here is that there are two kinds of mechanisms. We have the extrinsic mechanisms, alpha and beta, which describe the constraints of the system. I always consider the body as being part of the world. So when we see these simulations, we look at actually into the world and see the agent moving. This is actually a projection of the world state. So I consider the body being part of the world, which means that all morphological constraints of the body are included in alpha. So it's like a tiny symbol alpha, but there is much structure behind it. And beta is basically describes the sensory constraints of the system. And together they describe the constraints, the embodiment constraints of the agent. And this is fixed from outside. So the agent has its own embodiment, and that's fixed. But what is not fixed are the intrinsic mechanisms. So the internal dynamics of the agent and the policy. And if we talk about learning, then learning actually acts on the intrinsic mechanisms. So through adaptation of phi and pi, you can learn according to some principle, but this has to take place within the context, in the context of alpha and beta, in the context of the embodiment constraints. So now, if you have all the mechanisms, they give rise to the behavior. So basically, all the mechanisms generate a joint distribution on the whole sensorimotor loop. And then if you marginalize out all the intrinsic quantities, then you get this distribution on trajectories, which I condition on the initial state of the world and initial state of the initial internal state of the controller. And then you have a distribution of trajectories, future trajectories. And again, the behavior lives in the world, and it is. So when we specify the distribution of trajectories in the world, we specify the behavior. Although I have to say that I don't have a formal definition of behavior, but this is a kind of working definition to consider the distribution of trajectories in the world as being the behavioral repertoire of the agent. So now, as you can imagine, in this, the behavior is generated in terms of all mechanisms, which means that that it's actually in principle possible to find very simple intrinsic mechanisms that generate complex-looking behavioral patterns. Okay, so that's the important point, and the reason is. So let me explain the main idea that that the results I'm talking about is based on. So, for example, if you have a behavioral pattern here, it might be generated by different kinds of policies. So, two policies can be considered as equivalent if they generate the same behavior, and then we get an equivalence class of policies. And of course, we can choose among these equivalent policies the one that is least complex. And this is the general idea that I'm pursuing here. So I will exemplify this in the context of restricted Boltzmann machines. So let me, before I continue with restricted Boltzmann machines, say a few words on the information geometric approach, on the information geometric perspective of learning systems. So within information geometry, you consider the learning system, or you model the learning system as a manifold, which is basically the following idea. You have a set of parameters, which is the synaptic strength here, and if you modify these parameters, you basically modify the intrinsic mechanisms of the sensorimotor loop. If you go through all the parameters of the system, this generates a nice geometric object of intrinsic mechanisms in a usually higher dimensional space. And the main point of information geometry is that the spaces of mechanisms, conditional probability distributions, carry a natural geometric structure, and this can be inherited by the geometric object generated by these parameters. This leads in particular to the natural gradient method, where you have the Fisher metric defined in the space of all policies, and then you restrict it to the submanifold, and this gives you a nice metric on the manifold, which can be used for defining the learning algorithm. And it has been shown by Amari and many other people that it works quite well. So that's the approach to the information geometric approach to learning systems. So let me come to the geometry of condition-restricted Boltzmann machines. So a Boltzmann machine is graphically nothing but a bipartite graph. It consists of two layers of neurons, binary neurons here. One visible layer and one hidden layer, and each hidden element is connected with each visible element, and to this connection we assign a parameter wij, which stands for the synaptic strength between the element I in the hidden layer and element J in the visible layer. And then we add a so-called magnetization for all the elements. So this for the elements of the hidden layer, here denoted by HI, and for the elements of the visible layer, here denoted by VJ. So with these parameters, we have a nice probability distribution, joint probability distribution on the space of all units here. And geometrically, it's a nice object. It's called exponential family within information geometry, and this is one example of an exponential family, okay? Now, you are usually not interested in the hidden layer. What you want to have, you want to model a probability distribution on the visible layer, which means that you have to marginalize out the hidden layer. And this corresponds to this sum here. So you take the sum over all states of the hidden layer. What does it mean geometrically? Geometrically, it means that you take this nicely shaped manifold and project it down to a lower dimensional space. And suddenly it becomes very complicated. When people refer to restricted Boltzmann machines, they actually mean that projected geometric object. And many people try to understand that geometric object in order to understand the performance of learning. And it's very hard. It's even hard to determine the dimension of that projected exponential family. Until recently, it was an open problem to determine the dimension, and it has been solved by a colleague of mine, Guido Montefar, recently, using methods from algebraic geometry. So it's a very, very complicated object, but we can say a few things about that object. But before I continue, let me tell you how we use the restricted Boltzmann machines. So we don't use the restricted Boltzmann machines, we use a conditional version of them, which means that we subdivide the visible units into sensor units and actuator units. And taking this joint distribution on the visible units, we can compute the conditional, and this has also this nice structure here. And what cancels out is the magnetization of the sensor nodes. Okay, this cancels out after this conditioning. So now we can ask the following question. This is a model for the policy. Each element, each conditional distribution of this structure is an element of a polytope, of the polytope of stochastic matrices from the sensors to the actuators, okay? And this is usually a quite complicated, this forms a quite complicated geometric object. Now we can ask the question, how many hidden nodes do we actually need in order to model all policies, all elements in that polytope? That's referred to as the universal approximation property of the restricted Boltzmann machine. And this is actually the simple implication. In order to have universal approximation, in order to fill all the space of condition probability distributions living on this visible nodes, the number of parameters has to exceed the dimension. The number of parameters has to exceed the dimension of the polytope of all Markov matrices from k binary units to n binary units. Okay, and this is, so we count the number. We just count these parameters here and end up with this quantity. And the number of parameters is trivially greater than or equal to the dimension of that object, and then we require that that dimension equals the full dimension of the polytope. And this gives you a necessary criterion for universal approximation. So you cannot fill the whole polytope of conditional probability distributions without having m greater than this quantity. And this is, this is a disaster. It's exponential. You need really many, many parameters in order to fill it. And it becomes worse, actually. If you have that many hidden nodes, this does not actually mean that you fill the polytope. Usually what you have a more complicated geometric object sitting in the polytope of all stochastic matrices. By the way, I'm talking about the polytope of stochastic matrices because it's a Cartesian product of simplices. So if you have a stochastic matrix, each row is an element, is a probability distribution. It's an element of a simplex, and then you take the Cartesian product of simplices, and this gives you a more complicated polytope. So in particular, the extreme points are not affinely independent. So now I'm presenting this theorem here. It will not play a major role, but the reason I'm presenting it because it's quite non-trivial, and it took us 2 dissertations in order to prove that theorem. So if you have this geometric object, you want to estimate the approximation error. So you take a policy in that polytope, and you take the minimal distance. So how close can you come with your geometric object here, with your model, to that policy? It's this part here. And the distance is taken with respect to the Kullback-Leibler divergence. And then you consider the worst case situation. You take the supremum over all such policies, and this gives you the worst case distance of approximation in terms of this geometric object here, the condition restricted Boltzmann machine. And we were able to upper bound this maximal approximation error. And if you now set this upper bound to 0, which means you set you set this to 0. This means that you fill the whole polytope with this geometric object, and this gives you a sufficient condition for the universal approximation. So from this inequality here, from this estimate as a corollary, we get a sufficient condition for universal approximation, which means if m is greater than this bound here, which is greater than the bound that I have shown before, then you actually know you fill the whole polytope of conditional probability distribution. So if you want to model all policies, then you can be on the safe side if you choose m greater than this. So this is the geometry of restricted Boltzmann machine, conditional restricted Boltzmann machine. And I derived a necessary and sufficient condition for universal approximation. And the results illustrate a generic feature of connectionistic models. So they all have this nice property that you can do everything with them. You can generate any complex function with these simple elements. But the bad side of it is that you need exponentially many of them. And that's a big problem in this universal approximation business. But the question is, do we need that many hidden elements? And the answer I'm proposing here is that in the context of embodied systems, we don't need that exponential number of hidden elements. So what I'm going to show you is that if you actually exploit the properties of the body, then you can drastically reduce these exponential numbers. So that's the plan here. And the idea is the following. It's very simple. So what I have shown to you now is the policies. So I explained the main idea with this picture here. So you have the sensors and you have the actuators and you have the world, the outside world, and the transition from the world within one time step, from W to W prime, and here we have the mechanism alpha, and here we have the sensor mechanism beta. Pi is the policy. Now what I have shown to you in the previous slides is the, so to say, the attempt to model all policies from the sensor layer to the actuator layer, okay? But on the other hand, we are not interested in the policies, we are interested in the behaviors. So as I told you before, the behavior is taking place in the world. So if two policies from S to A generate the same behavior from, in other words, the same transition from W to W prime, then we shouldn't model both of them. So we can take one representative within that class, which gives us a lower dimensional projection of the polytope of all policies, and the stronger the embodiment constraints, the stronger that projection. Okay, the lower dimensional, the image of that projection. So this is what I just said in formal terms. So we have the policy behavior map, which assigns to each policy a transition from W to W prime. So that's the transition from W to W prime, and this is the formula for it in terms of the mechanisms. We see the sensor mechanism, and we see, so which is here, and we see the, oh, so what's that? And we see the transition of the world alpha on this side. And if you consider both of them as being constant, as I said in the beginning, they define the embodiment, then this function is linear in pi. So it's really a linear projection from pi to the space of all conditional distributions from W to W prime. And we can compute the dimension of the image of that map. So many policies will be mapped to the same behavior. So we can compute the dimension, and we call this dimension the embodiment dimension. Okay? And instead of universal approximation, we talk about embodied universal approximation, which means that a model which parameterizes policies from S to A is called an embodied universal approximator, so M is the model, if it can approximate all behaviors that the system can in principle generate. Okay? And so here's an image of an embodied universal approximator. So here we have the polytope of all matrices from S to A. This is basically this huge dimensional object that I was talking about before. So if you want to model all policies within that polytope, you need an exponential number of hidden nodes. But now we map this through this embodiment policy behavior map to a lower dimensional space of transitions from W to W prime. So these transitions. So this object has the dimension d alpha beta, which is the embodiment dimension. And as I said, this will be low dimensional in strongly embodied systems. Now, instead of modeling all elements here, we reduce that set to a smaller dimensional set M, which gives you the same shadow, so to say. That's what's written here in this equation. And it turns out that you can explicitly write down a model, it's this one here, which gives you that. So the dimensionality of your model is exactly the dimension, so I forgot to write, so this D is actually the D alpha beta. So you only need as many feature vectors here as the embodiment dimension of the system, okay? So that's nice. The problem is that the feature vectors themselves can be very complex. So we have an explicit formula how to write down the feature vectors, but they involve some information about the embodiment, and it's quite complicated to write them down. And I think, so we shift somehow, we reduce the complexity in terms of dimension, so this is the optimal we can do. But at the same time, we increase complexity in terms of the feature vectors. Mm-hmm.
Could you explain the relation between E and beta and alpha?
This one, yeah. I would need more time for that. We have explicit formulas for the feature vectors here. So all I want to say is that it's in principle possible, and you can write them down. But they would involve information, and this is how I now motivate. I'm coming back to the restricted Boltzmann machines because I want some reference architecture with which I want to do the embodied universal approximation instead of working with these feature vectors. But I want to mention that we can actually reduce the complexity, the number of feature vectors to the number of the embodiment dimension.
So it's simply the outer product. It's not simply the outer product of alpha beta.
No. It's some kind of product, but not, it's not that simple. So from now on, I replace the general, I assume this architecture here, which is the restricted Boltzmann machine. Yeah, okay, I don't know. Okay, so this is the architecture I'm assuming here, and we interpret the condition restricted Boltzmann machine in a generative way here. So you read it.
Only the display.
Okay, yeah, okay. Thank you. So we measure the sensor values and then we fix them here. We update the hidden layer, and then after that we update the actuator layer and then the hidden layer again, and this is Gibbs sampling. So you do it several times, and after a few steps you read out the actuator values and give them back to the work. That's the generative way of using the condition restricted Boltzmann machine. Okay, so now this is my results, a result on embodied universal approximation using restricted Boltzmann machine, condition restricted Boltzmann machines. So first of all, let me introduce this quantity here, because it's also assigned to the embodiment of the system. So basically, if you have sensors, usually multiple sensors, you will have some redundancy among the sensors. So you basically, not all states of the sensors are possible when you read them out from the world. So we count the number of sensor states that can actually be, that have non-zero probability. So that's the S beta, but this is a technical detail. It doesn't play an important role here. So the important point is, if you want to model all policies from S to A, then you need a number of hidden nodes that exceeds this number here. So which is the necessary condition that I had derived before for the universal approximation. But now if you use the embodiment constraints, so you don't want to model all policies, but you want to model all possible behaviors from W to W prime, then this reduces to a sufficient number lower bounded by this cardinality of the possible sensor states plus the embodiment dimension minus 1. Okay? So I'm going to convince you that, I will try to convince you that this is actually a strong reduction in an experimental case study. So let us apply this, okay? So this is the robot that we are working with. So how many minutes?
10 minutes.
10 minutes, okay. The robot that we are working with, it has 6 legs. Each leg has 2 degrees of freedom, the shoulder and the knee. And each angular range is discretized into 16 states, which is modeled in terms of a binary vector of length 4. Okay? So we have the 16 states here, and we assign these binary vectors to the discretized states. And so in other words, for each degree of freedom, we have 4 binary neurons. This gives us, as the number of sensors and number of actuators, 48, which means that the state space of the sensors and the state space of the actuator is 2 to the 48, which is a huge number. Now, I want to show you I'm sorry. So you want to generate that behavior of the agent. This is a kind of target behavior. What you see here is not generated with a restricted Boltzmann machine. It's really open loop control, so we set it from outside. It's a sign controller, and the symmetry of this hexapod allows us actually to generate that behavior. And we want to do that, to mimic that behavior in terms of a restricted Boltzmann machine. Now, if we let me show you how many hidden nodes we would need in the context of embodied universal approximation and how we will need in order to generate that behavior in the embodied system. So in order to do so, we count the number of sensor states. So if you remember this S beta, it's the number of possible sensor states. And so here's a histogram of all sensor states, and here's the wishy-washy part of this strategy. We simply take, I think, 80% of the sensor possible sensor states. Okay, we have no reason for that. Okay, this is just to and this gives us 63 sensor values. We could try to interpret the other sensor values as sensor states as noise or generated by noise. So then we
80% of 2 to the 48, or 80%?
80%. So we let the agent walk, then record all the sensor states and count how many times they actually occur. For this behavior, they live in the space 2 to the 48. But it's of course a much more reduced number of sensor states because we refer only to that behavior. And from that histogram, we take 80%, okay? So this is the 63 sensor states. We compute for this walking behavior the embodiment dimension. It turns out that it's 3. Subtract the -1. So according to our theorem, it says that if we have m, the number of hidden nodes, greater than or equal to 65, we will be able to generate that behavior. If you compare this with the non-embodied universal approximation for k equals n equals 48, we get m greater than or equal to, greater than 10 to the 14. So it's a huge reduction of complexity if we use the embodiment information. And let us test it. So this is this poor guy. This is, describes the sensor states. These are 48 sensor states, 48 actuator states, and this is the hidden layer. It only consists of 5 neurons. Let's start with 5. So m equals 5. And we trained the system. I'm not going to show you the training phase of. And you see that the guy is not able to generate that reference behavior, which is shown as a transparent body here. So this is what the best it can do with its 5 neurons. Now let us give the agent the 65 that our theory predicts as being sufficient. So here we have the 65. Let the system run. This is actually the activity of the brain, of the condition-restricted Boltzmann machine. And you see it's much better now. It comes close to the reference behavior. I have to note that the reference behavior, as I told you before, is set from outside. So it's not at all clear that you can model that behavior with respect to a condition-restricted Boltzmann machine. It turns out that you can't. You can come close to it, but you can't do it exactly. You will see in a second. So this is with the 65. And then we looked at all possible, up to 100 hidden nodes. So we started, so this is the plot from 5 hidden nodes to 100. And here we have the 65. And the performance, this is the performance of the walking behavior in terms of meters within 30 seconds. So if you start with 5 hidden nodes, it doesn't perform well. Then you increase the number of hidden nodes, and you see that it is already optimal slightly below 65, but when you reach the 65, it is saturated already. And you see that there is no further benefit if you increase the number. So it comes close to the ideal walking behavior, but you also see with this plot here that it never reaches that ideal behavior. So this is the discrepancy between this behavior that we want to model and the modeling architecture. But in principle, I was very happy to see it, that this geometric approach is quite powerful in giving us the right number of hidden nodes that we need in order to generate the target behavior while exploiting the embodiment constraints. So I won't go into the details of the Umwelt concept. So that would have been the second part, but we don't have the time for it. But I hope that I could convince you that geometry, and in particular information geometry, is quite a powerful tool to model learning systems, and in particular to understand how embodied systems can actually exploit their embodiment constraints to generate behaviors. Thank you very much.